This is a Rich 9329 tutorial clip on amines. Amines are organic molecules. They have a alkyl chain, carbon chain, and then they have the NH2 attachment. Now amines can be primary, secondary or tertiary. This is dependent upon the number of alkyl groups attached to the N atom. So example 1 is the primary amine, methylamine. Methylamine has the methyl group attached to the nitrogen group. There is only one carbon attached, hence primary amine. The second amine is a secondary amine. It has two carbons attached. They are both methyls, hence dimethylamine. The third classification of amines is the tertiary amines. This one, there are 1, 2, 3 methyl groups attached, so trimethylamine. Next we'll go on to naming amines. The alkyl groups attached are placed in alphabetical order. Here are 4 examples. The first one, I've noticed a mistake. Brilliant. Ethyl goes first, then methyl next, and propyl third. So it should read ethyl, methyl, propyl amine. Next, that's correct. We've got an ethyl. We've got 2 methyls attached to the nitrogen in the center, so that one's a tertiary amine. So it's in order of the attachment, so ethyl, dimethylamine. The third one is a benzene ring based amine. It's called phenylamine. The third one has a methyl group attached. It has a phenyl group attached, C6H5, and so its name is methylphenylamine. Now a couple of physical properties for you to consider. First of all, comparing the boiling point of methylamine versus methanol. So methanol has a higher boiling point. It has stronger hydrogen bond intermolecular forces than the methylamine molecules. This is because there's a more significant difference in the electronegativity values in methanol than in methylamine. This leads to a stronger intermolecular force. Finally, on this first clip of the amines, we're going to consider the solubility in water. Now, propylamine and methylamine and ethylamine as well, they are all soluble in water, and yet phenylamine is insoluble in water. That's because propylamine here, it can form a hydrogen bond with water very easily. It has a short alkyl chain, so the main intermolecular force is within the propylamine is still hydrogen bonding. But this is phenylamine. It is insoluble in water. So it doesn't dissolve, it is immiscible. It's immiscible because it has van der Waals intermolecular forces which are very strong, and so the water, which is hydrogen bonding, cannot mix with the molecule. This is amines part 2. So the chemical properties of the amines, they can act as nucleophiles. They have a lone pair of electrons on the nitrogen which can attack a delta positive carbon with the loss of a bromide ion. So the amine acts as an electron pair donor nucleophile. They can also act as bases because the amine can accept a proton and behave as a Bronsted-Lowry base and be a proton acceptor, a bit like ammonium. Now phenylamine, so C6H5NH2, can react with HCl to form this phenyl ammonium chloride. So you can see that the amine group has reacted with the H+, and so again is acting as a base. Now you can reform the phenylamine with the reaction of ammonia. So ammonia is a stronger base than the phenylamine, and so removes the proton from this phenylammonium ion, forming phenylamine and ammonium chloride, the byproduct. Comparing the base strengths of the amines. Now you can see down the bottom, what I'm going to try and clarify to you here is that the methylamine has a different base strength to this base, and also to the phenylamine as well. And that depends on a couple of things. The first thing it depends on is the availability of the lone pair. The second thing it depends on is how many alkyl groups are attached. So if dimethylamine has got 2 methyl groups attached, so it has more methyl groups to donate the electron density to the nitrogen. So there's a greater amount of the positive inductive effect than the methylamine. Now the other factor to consider is solubility. So dimethylamine, because it has these 2 carbon groups, it's not going to be as soluble as methylamine. As you know, there's more van der Waals forces with dimethylamine, and hence I've written medium solubility. Now with trimethylamine, the solubility is going to be even less. The methyl groups, this van der Waals forces are going to be stronger between 2 molecules of trimethylamine, and there's less of a chance that it will dissolve in the water and actually pick up a proton which can be found in the solution. And so therefore dimethylamine is a stronger base than trimethylamine. It's a stronger base than methylamine. So you have to consider those 2 factors: the positive inductive effect and how soluble the base is. Now phenylamine, the last one here, is a weaker base than ammonia. So this benzene ring actually pulls in the lone pair of electrons on the nitrogen into the benzene ring, into the delocalized structure. So this is called the negative inductive effect. I've shown that with the arrow here. It's pulling the lone pair in, making it less available, and so phenylamine is the weaker base. So these molecules here, we consider the positive inductive effect, but also the solubility. Phenylamine, we consider the negative inductive effect. It also has low solubility because it's the benzene ring.